Right. I will keep it short. Yeah, thanks for coming and attending this workshop. It was a pleasure to organize it with John and Judd. We have a couple of talks, so we try to get a good mix of different perspectives on market design. And we're very happy to have Zhuoran give the first talk. She's assistant professor here at Yale in statistics and data science. Was a postdoc, I believe, previously at in Berkeley, PhD from Princeton. I think working very interesting work on kind of the intersection of machine learning, like particularly deep learning, and economics, which I think fits very well with this conference. I'm very happy that you're here. You can give this talk.
And thank you, Paul, for the kind introduction. And it's a great pleasure to be here. And I'm a Yale local, so welcome everyone to Yale. This is today I'm going to talk about our recent work on using language model for decision making. And this is
just when you have a problem, the lady left.
So just have to click on it once. I think that usually works afterwards. Can you try again?
Yeah. Okay. So this is the paper has this title. This is joint work with Chuan Hao, who is a postdoc at Yale, and he's also in the audience. And he did most of the work. And Reihan, Tiankai, Mila, Korush are undergrad students who helped with some experiments. And Dirk is a senior faculty member here at Yale. And the code, this paper is on arXiv and with the link in the QR code. My agenda is today is to help you try to explain this our algorithm framework. And to do that, I want to first talk about some background and talk about the background of how what are the challenges when we directly use language model for decision making, and and some challenges are actually intrinsic. And then I would like to introduce our framework and with some examples. And so let's directly jump to the problem. So we want to language model right now is a buzzword. We all and it's a surprising AI model which is able to talk like a human and maybe think like a human. And human beings make decisions every day. So a natural idea is to deploy those models for decision-making problems. There are some success stories. One of them is called the Cicero, which is an AI model developed by Meta AI. And they use language model for solving a game called diplomacy, where language model play as a player, it takes a role of a country and interact with other human player and also AI players. And this game involves strategic plays, including cooperation and conflict. And another example is called Hugging GPT, which is a recent paper where the researchers use ChatGPT, which is a language model for solving tasks. And the task is specified by human. Well, the interesting thing about this model is that language model right now serve as a task planner. And that is when the human specify a task. I'm not sure if you can see this. So here it, well, sorry. So here the human says, can you describe what this picture depicts and count how many objects in the picture? So this is a task. Given this, and then the human, the user feed a picture. Then the language model sees this and then specify what are the tools I need to accomplish this task. And so language model does the thinking. And then it calls the model from a website called Hugging Face, which is a website containing a lot of machine learning models. And then the ChatGPT directly select which model to choose and deploy this model, and then get the result and summarize the result and return to the human. So these are two success stories. But there are also some challenges. I will talk about 3 failure modes. The first one is called hallucination. Well, hallucination, this is an illustration. It might not be the true response you get from ChatGPT because it's keep evolving and every day it's getting better. But there are 2 types of hallucination. The first one is about fact. That is, the language model might fabricate some unverifiable or maybe false fact. And the other kind is called faithfulness hallucination. That means it has 2 kinds. The first kind is called instructional or contextual hallucination. That means you might describe a sequence, some complicated instructions or context informations, but in the output, language model just neglects some of them, or maybe just violates the instruction. And there are also some logical inconsistency, which means that when doing logical deduction, it comes with error. And I tried to come up with an example to illustrate this last week. And the last one is the prompt I sent to ChatGPT. Ask it to give me an example of EC'24. That is, give me four numbers and using some arithmetic operations, come up with number 24. And additionally, I have a few instructions. I want the answer to be written in LaTeX, and also repeat my question and in blue color and have the answers all in red color. And this is the answer I get from ChatGPT. And it's of course it's a LaTeX code. And then I compile it, and what I get is as follows. It fails to follow all the instructions because part of the answer is written in red. Believe me, this is actually the answer I get. And so it has this instructional inconsistency. And more importantly, the answer is wrong. These numbers cannot get me 24. They got 18. So we have two of these hallucinations. So language model can really hallucinate. Another failure mode is exploration, because we want to eventually deploy them for decision-making problems. In online decision-making, a fundamental challenge is exploration. We have a few choices to choose from, and we need to try all of them at least once in order to reduce uncertainty. Well, when we deploy, one of the toy model is multi-arm-banded. So there is a recent paper where researchers deploy GPT-4 on 5-arm-banded problems, and they calculated regret. Well, the answer they got is very sensitive to the exact way you interact with the language model. And they identified that there's one way they have success, where in this way, they need to explicitly tell the language model that you need to explore. And also, instead of storing all the history, you store only the summary statistics, that is the average reward for each arm. And then in the prompt, you need to use a specialized prompt called chain of thought, which we will come back later. And all other configurations have a large regret, which is in the left figure, where the regret of GPT-4 is the average reward of GPT-4 is the blue curve, which is strictly lower than the benchmark, say UCB and Thompson sampling. So this is another failure mode where language model cannot robustly explore. And the last one is about mathematics. So this is exactly the left-hand side is the prompt I wrote to GPT-4. This is also the experiment I did last week. And then this is two-number multiplication. The numbers are very long. Well, and they are just typed in as a character, as a language string. Well, then the first one is from ChatGPT 3.5. It gave me a wrong answer. The second one is correct answer. It's given by the latest model, GPT 4.0. And the last one is given by Anthropic Cloud, which is another very popular language model. It's also wrong. Also, it gave some derivation, but the answer is wrong. Okay, you might wonder, well, you might think maybe the second one, well, it's good because it gave me the correct answer. But if you stare at it for a few seconds, you will realize, well, actually the way they got the number GPT 4.0, GPT 4.0 got the correct answer is by secretly calculating the answer using Python. So language model itself cannot reliably perform calculations. Okay, now I would like to talk about our framework. We try to avoid, or we try to resolve these challenges by including two additional components, a set of tools, and also a working memory. So it has three components: a language model, and a set of tools, and a working memory. The language model does the reasoning part. It tries to emulate some algorithm, and the tools is some take over carry out the low level actions like calculating numbers, and there are some Python functions that we write specifically to each applications. And working memory just stores the intermediate results you get when you solve the problem. Well, so how do we address these challenges? And so the language model do not interact directly with the underlying environment in the decision-making problem. Instead, it calls a bunch of tools. It only decides which tool to use, and the tools directly take the low-level actions that interact with the underlying world. And the language model handles the reasoning part. So language model, the thought process, which is some the building blocks of the language model, which describes which algorithm you use, and it can directly inject the need of exploration. And about mathematics, these calculations are carried over by the tools. So these are Python functions are reliable. And to reduce hallucination, we save all the intermediate results into the memory. So this is a whole framework. And also another property we get by separating the physical world with the thought world is that now the complexity involved in language model decision-making is independent with the size of the problem. So no matter, just consider the bounded problem, I just want the language model to understand the idea of UCB or Thompson sampling. And the complexity of this thought, this idea, is independent of the number of arms we have. So that's the byproduct we have by doing this separation. And there's a demo where we apply this to a simulated world, a simulated environment of autonomous driving. It's called highway in, where the goal is to just change lanes and keep driving. And our method stay in the road much longer than the benchmark, where benchmark just you can see it collides easily. So now I would like to take a step back and just motivate you why we want to come up with this framework. And so let's look at the basics of language model. So language model is, well, right now we often use decoder-only language model, which is just autoregressive language model. That is well, mathematically, we can just view this as a conditional distribution. Given a sequence of a language prompt, it outputs the next token. A token can be viewed as a word. And in terms of architecture, because it's just a conditional probability distribution, given a sequence of words form a conditional distribution over the next word. So the input is a set of discrete objects. So we need to embed them into vector space. That's why in the bottom layer we have some embedding. And then upon the embedding, we have some attention layer, which is the main building block of transformer. And then there are some other layers, including fully connected layer, residual layer, and some normalization layer. And then we have some vector, how to transform it into a distribution. We have a softmax transformation. Okay, so this slide is about the softmax attention mechanism. I will just skip this. So language model is just a conditional distribution. How do we, some neural network which implements this conditional distribution? How to train them? The training involves two stages. The first one is called pre-training, where we just gather diverse sources of text data and train to predict next token. The data, say, include stack exchange and also Wikipedia data. And the training, the loss function is just MLE. And then after that, the language model only knows how to complete a task. How to enable it to chat with human, we additionally need to do some fine tuning. And this is done by collecting some questions and answers, having these pairs and solve a supervised learning problem. So in summary, training a language model just means that we want to collect some data and fit an MLE. And then just consider, say, suppose our number of data gets to infinity, what we can expect is that language model will learn the underlying distribution of the training data. And then after that, the language model is fixed, and we will just use them. How do we use them? We interact with them by prompts. That is, we send some text and try to get the output. And prompt engineering is really art. The way we interact with them makes a lot of difference. There are some keywords that are really magic. For example, let's think, if you write your prompt with let's think step by step, the output will have this multi-step reasoning structure. And there's also another one, let's take a deep breath and work on this problem step by step. It works magically very well for optimization problems. Well, this is art, but let's revisit the three challenges, why they appear. Why it can hallucinate is because language model is just a conditional probability distribution. When you generate from a conditional distribution, it's stochastic. So of course we cannot control the randomness of the world. It will hallucinate, generate some random number, random answer. Why it cannot explore is because the pre-training data is not coming from data collected from an online decision-making problem. The data does not contain, is not explorative enough. And there's another follow-up paper, another recent paper which directly collect data from online decision-making problems with exploration and train a transformer from scratch, and then deploy it on bounded problem. Suddenly it works very well. That's because the data is explorative. Then when you imitate the data, you get a good result. You have this exploration behavior. And why you cannot compute math is because language models store the number actually as tokens and generate the answer by token by token. It doesn't understand the math. It just understands how to complete the next token. And there are some principled ways of prompting the language model. Eventually I want to come to chain of thought. The basic method is called in-context learning. It's just a fancy way of saying that when we want to induce certain behaviors, we first gave a bunch of examples. And this example is a bit small. It is some sentiment analysis. You give a few sentences, each sentence, you have a positive or negative label. And you give 3 examples and ask, what is the label associated with the sentence? It doesn't work. It should be negative. And so the prompt structure looks like this. You have a bunch of questions and answers, input and output examples. And so there are 2 examples and an additional question. And you expect to have the correct answer. So this is called in-context learning because learning happens during inference time when the language model has fixed parameters. And the prompt, you might prompt the language model with some very strange questions and answers. And that might not be part of the training data. But language model is able to, in many cases, is able to extract the concept from these examples and get the correct answer. And there are some, this method only works for simple problem where you have a very clean input question and answer structure. And the reasoning logic is simple. And there are a lot of papers try to understand why it works. And one answer they have is that it's doing Bayesian inference. The idea is when you have the prompt, the examples in the prompt, it infers what is the latent task. And use that behavior and form this posterior distribution over the task. And on this new input, xn+1, it outputs the answer according to the task, and then aggregate over the posterior. And this, actually, you can prove this if you, assuming the Gaussian linear model and train a transformer by predicting the next token. And also empirically, people verify this by training on linear data. And there are 2 lines which align very well. The red line is the transformer, the error you get from transformer from in-context learning. And the dotted line is the optimally weighted ridge regression, which just corresponds to the Bayesian estimator in this case. So these 2 lines align very well. And how to extend this idea to more complicated reasoning problems, a useful method is called chain of thought, which is very simple. It just means that instead of just giving the input, the questions and answers, you also prompt with intermediate results. And this is an example. So the answer So in the prompt, when it gives the answer is 11. Additionally, it has the intermediate result in the blue color. Roger started with 5 balls, 2 cans, and 3 tennis balls. Each is 6 tennis balls, and 5 plus 6 is equal to 11. So it includes the intermediate reasoning steps. By having them, then the language model can try to understand what is the reasoning logic you have to arrive at the answer. Also this method does not address the challenge of hallucination. Actually, it perhaps make it worse. The reason is now you have a longer reasoning chain, and then you need to make sure each step is correct. Then the answer is correct. If a single step is wrong, then the whole reasoning trajectory will just go to somewhere else. And there are other improvements based on chain of thought, which tries to address the hallucination problem. They want to do some token selection, and that one simple way is to do majority vote. That is, we simulate multiple reasoning chains and do a majority vote. Or you can do a tree search in each step. And so this is an active area of research currently. And now let's come to decision-making problem. The goal we have is to deploy language model for sequential decision-making problems in the real world. So language model specifies a sequence of actions that can be deployed to the physical world. And these actions, the most ambitious goal is to deploy physical actions that can, for example, robotic actions, the actuators, and then process the observation obtained from the real world. And the caveat is that language model only works in language space and cannot take physical actions, and it cannot perceive information beyond text. For example, if the observation is image, it cannot process the information. So how do? We want to add additional components. We want to add a set of tools to take actions in the physical world. And also we want to have a processor which transforms the observation in other modality into text. So then we have this 3-component structure, a planner, which is a language model, which chooses which tools to use. This is some high-level planning. And then the actor is a tool which does low-level actions. And these low-level actions will generate some observations. It's processed by the perceptor, by the reporter, which transforms, say, the image into a text summary. And this text summary is prompted back to the language model. Then, under this framework, in terms of prompt engineering, what we need to design is actually how to select the tools and how to summarize the observations. And a baseline method for language model for solving using language model for solving decision-making problem is called React, and we build upon this framework. React only considers decision-making problem described in language domain, and the idea is simple. It just combines chain of thought with a sequence of actions. So that is, before taking actions, it first generates a sequence of thought, try to understand why we take this action. And how to induce this thought action structure is by writing a special prompt. And for example, in this prompt, this one is a question, and the standard answer is just a standard way of, if you directly prompt it to a language model, it will give the answer. And if you reason a chain of thought, just add a reasoning step that is in this red color. And if you only have act, then that means in your prompt, you only give a sequence of actions in order to achieve the final answer. And React combines chain of thought with a sequence of actions. So in the prompt, it first writes thought 1, which is the first thought. And then after this thought, it will come up with the action, get the observation, and then use this observation to come up with the next thought, and then the next action, etc. And the actions in this special problem include search, lookup, and finish. Finish means that we just conclude. And this is actions interacting with the Wikipedia environment. And a prompt looks like this. This is a system prompt. It specifies 3 actions. And also it says that we have a thought, action, observation structure. And then this is the one example of the in-context learning. It's a chain of thought example. So it has a thought, action, observation structure, decomposing the logic each step. And the challenge is that sometimes the thought logic, especially when each step, each action does not have a informative response. That is, you have a sparse reward. Then the reasoning logic can be very might not be robust, and it will just circle around and around and cannot jump, be trapped at some point and cannot jump out of the loop. And the reason is this thought logic is based on common sense reasoning. It doesn't specify what is the rationale underlying the sequence of actions. And this common sense reasoning might lead to hallucination. And so that's why we want to include a special way of generating the thought by encoding the algorithm into the thought and using tools to take the actions. And use the working memory to store the intermediate result to reduce hallucination. So this is I would directly talk about tools. Tools just specifies based on pre-described Python functions that are able to achieve some functionalities. And combining these these tools might specify a sequence of low-level actions. And for example, if you solve the MDP, the tools consist of, say, updating the Q function and updating the value function and get the greedy actions from the Q function. But the value of the Q function is stored in the memory. And the reasoning process is the prompt we write for language model. It is used to emulate some algorithm. It consists of a sequence of thought units because our algorithm can be iterative. The algorithm can be, say, dynamic programming for solving MDP and UCB algorithm for solving online MDP. And each thought unit consists of a text and which describes the reasoning logic. And also a sequence of operations, that is a sequence of tools, the name of the tools to be executed in order to implement this logic. And then a binary variable which indicates, which is a flag for termination. So these are all language-based, and it's a part of the prompt. So for example, one thought process can be, say, doing one step of dynamic programming. And for example, this is in this prompt, in this thought unit, the text gives us a description of dynamic programming, one step of dynamic programming. Let's do value iteration and starting from the last step. And then the operations we need to call is to update the Q function and update the value function, and then exit. And the intuition is that each thought unit, we want the language model to imitate one step of an iteration algorithm. And then by specifying a sequence of iterations, then we can just emulate some desired algorithm. And then this algorithm solves the task. And tools can interact with a working memory. And we use two kinds of memories. Well, there are two kinds of memories. The first one is the memory of context. That is the information stored within the prompt. And also, we additionally use a working memory. So working memory is used to store the intermediate result. That is, for example, the reward function, the transition model, the number of actions, number of state, these parameters of the problem, and also the intermediate results, like the Q functions and the value and the V functions calculated in each step. So actually, the complexity of the problem that is how large the underlying problem is reflected by the size of the working memory. It's independent with the complexity of the thought process. And this is an example of the value iteration algorithm. So the first value iteration is an algorithm for solving MDP, where you go from the last time step to the first time step. So the first thought is to start from the last step, which is capital H. We calculate the Q function and value function. And then we go to the next step, the H-1 until the first step. And then after calculating the value functions, we now take the actions by applying the greedy actions from step 1 to step H. And if you execute the greedy action, then you get the optional action sequence. So the tools include update these functions for updating the value functions and take the greedy actions. And these tools and the working memory store the parameters and the intermediate result, which is interacting with the tools. And one example of this prompt, for example, in the system prompt, that is before the examples, before everything, we first describe the problem, which is a MDP with horizon 5 and number of five states and 5 actions. And we explicitly tell the language model that it can interact with the parameters are stored in the working memory. And then this is the prompt of each thought unit. In the thought unit, we first have a thought. This structure is very similar to React. We have a thought and action and get a result. So the thought just tells explain the logic of value creation and also call the tools. The tools are in boldface and in blue color. And the operations is about calling this function with input. And then the result is the Q function we obtain by running this value function. And then we just, after that, this is one action we need to, this is one substep of one iteration of value iteration. We first calculate the Q function, then update the value function. So there are 2 operations. So after having a Q function, we then call update V to get a V function, etc. And this is just part of the prompt. And so the whole prompt, you can imagine, it consists of multiple thought units just to run this value iteration. And then after having this prompt, we just test it on a new MDP instance, which have a different hyperparameters. So here we have 5 number of steps. We can test it on, say, 10 steps and evaluate how good it is. So in summary, in this framework, we just separate the low-level action with high-level actions. The low-level actions are implemented by the tools, and the reasoning, which are the sequence of tools that we need to use in order to run some algorithm, is done by prompting the language model. And in this way, the complexity of language model reasoning is independent of the size of the problem. And it can be deployed to other cases, say handling vision-based tasks or multi-agent tasks, just by writing different tools. And this is one example. I will briefly talk about 2 examples. The first one is a bargaining game, where the buyer and sellers just negotiate, and they have different evaluations. They want to achieve some consensus about the price. And we assume that there are T rounds of total number of rounds of bargaining, and there's a discount factor, maybe different for each player. And if they don't reach a consensus, both of them have 0 utility. So the optional price of this problem can be computed by dynamic programming. I will not talk about details, but we can see this is a result we have by running our algorithm and aggregate over 20 independent runs. And we ask our model to play with itself. So the ideal goal is to converge to the subgate perfect equilibrium. So as we can see, the frequency of the success rate of converging to the equilibrium is pretty high for our algorithm. And the benchmark algorithm involves a chain of thought and chain of thought with Python code. So that is GPT-4 right now can just directly write Python code in itself, and also few shot chain of thought. That is chain of thought including more examples. And interesting thing is that when language model can write code, actually it performs worse. The reason is the code they write is not correct. And also you can see that the frequency of achieving equilibrium is much lower. Also, so I will skip the prompt in the interest of time. We can also like it to play with the baseline algorithms. So here, this is a result. We play with zero-shot chain of thought, and we can use our method as both the buyer and seller. And as a buyer, and because it's the opponent is imperfect, we can actually leverage this irrationality of the player and get a better result, no matter it's for the buyer and as a buyer or as a seller. We both got a better result than the equilibrium. And also we can apply our method to the incomplete information scenario where the buyer's value is unknown, and we need to directly infer it and use the belief aggregate the belief for decision making. And again, here we have the solution concept is sequential equilibrium, and we have a higher probability of reaching the sequential equilibrium. And this is another example is online learning of MDP. I would just directly show you the result. This is for knowing the MDP model and calculating the optimal policy. We have a very high probability of finding the optimal policy just by running the emulating dynamic programming algorithm. And if in the online world where we don't know the model, the transition probability and the reward function, and need to estimate from data, then our method perform on par with the benchmark, the state-of-the-art benchmark, which is UCB-VI algorithm, and it performs much better than the other benchmark language model-based methods. And also, I want to note that UCB-VI involves exploration, and exploration is achieved in our case by explicitly write in the thought unit to ask the language model to compute the bonus function. And this is the demo on heavy imp I just showed. So I want to conclude in the interest of time. So I will talk about our framework, which is called Stride. It has 3 components: language model-based reasoning, and a set of tools, and also some working memory. And we will explicitly separate the reasoning, the high-level reasoning of language model and low-level actions in the physical world. And by doing that, we can get flexibility, and also we address the challenge of exploration by directly write exploration in the language model reasoning and reduce hallucination by having a memory. And also the mathematical calculation is done by the tools. Okay, thank you.